and the thick lens, because it's just quite tricky and there are a lot of concepts that we have to deal and we have to understand. So I will give three books, which is my favorite books, at the last of the video. Just move on. So what is thick lens? We consider thickness is a negligible component in case of thin lens in our previous video. But in thick lens, when the lens thickness is comparable, when lens thickness is comparable in magnitude of the radii of curvature, or the focal length of the lens is no longer thin. So this is the beautiful definition. You have to understand that when the lens thickness is comparable, so it's very important to understand, when the lens thickness is comparable to the either radii of the curvature or the focal length of the lens, so then lens is no longer thin lens, so then thickness matters. Or in another way we can think this thing is a very important component. We can assume that the physical lens is thin only, just remember, only if thickness is less than one tenth of radii of curvature. It's very important point to understand. This is a very important definition. Or thickness is less by one tenth of focal length. So it's very important. If focal length is very short and the thickness is high, then it's considered thick lens. So we always consider IOL as a thick lens. We always consider contact lens as a thick lens. So it's important why we consider it as a thick lens, where the comparability of radii of curvature or focal length. So one of the rough idea you can take is this. It's not absolute, but rough idea. It's very important that you understand this concept when you talk about thick lens. Why you say some lenses are thick and why you say some lenses are thin. It's very important. Okay, so let's move towards the, when we are talking about thick lens, then we talk about the cardinal points. The cardinal points is very important points. With the help of cardinal points, we take a lot of ideas about the equivalent power, ideas about the how we going to draw pictures, draw tracing rays in case of thick lens. So in case of thin lens, we talk about it in previous videos, but in case of thick lens, we have to talk about the cardinal points. And typically, we talk about six cardinal points, which is primary and secondary focal point. We have discussed about it in previous video, and we will discuss about the primary focal point, secondary primary principal point, secondary principal point, primary nodal point, and secondary nodal point, and how these points make changes in our understanding of optics. It's very important to understand every point. So primary and secondary focal point is same as we have discussed. The primary focal point is defined as the on-axis object point and resultant plane wave when leaving the lens, and secondary focal point is simple, when parallel lights come to the system and it hits and then it focuses there. So it's simple thing, something like that. Primary focal point, when light leaves from there and it strikes and then goes parallel. This is simple term, is a primary focal point. So is front focal length, which is focal length from the vertex, and from principal point is equivalent focal length. So it's quite two different terms, but we will discuss in later. But at the same time, secondary focal point, when light comes parallel from the infinity parallel to the optical axis, then it focuses. Where it focuses is secondary focal point, and the distance from vertex is back vertex focal length and effective focal length. It's simple thing. From the, this is principal plane. So let's discuss. So cardinal points, principal plane, and now this is very important. Principal plane, the imaginary plane along which the refraction was assumed to be happen. This is first imaginary plane, and the second important point that we have to understand, refraction was assumed to be happen when plane wave from leaving primary principal plane or plane wave from incident from secondary principal plane perpendicular to the optical axis, because this plane is perpendicular to optical axis. This is the plane. The intersection point of the primary principal plane and the optical axis is called primary principal point. This point where primary principal plane interact with the optical axis is called, this point is called primary principal point, and at the same time secondary principal point is same concept. All distance relating to optical system are measured from the principal plane. This is very important point. If you are talking about thick lenses, then you must understand if all the distance, that focal point and all things distances, especially focal lengths, we take distance from the principal plane. It's a central important concept you have to understand. So again, that's that figure. This is the principal plane, and how you will draw this? If from the primary point, principal point, light goes like this, and then it bends from one surface, and then again it bends from another surface. We just dot the two dot the line from two surface. From back we keep back, from front we keep going on, and then when it meet, then we just draw the line which is perpendicular to the optical axis, and this line is principal, primary principal plane. Secondary principal plane is related to secondary focal point, definitely in primary principal point relation to primary focal point. So when parallel light comes, it bend from first surface and it again bend from second surface. Then we draw the line, parallel line, we just extend it, and from back surface refraction rays we extend from here, and when it meet, then we draw the line. This line meets at the secondary, meets at optical axis, which point we call secondary principal point. So this is the secondary focal point. So it's, by drawing is simple, but we have to understand this is very important because all the measurement taken from the principal plane in case of thick lens, it's central important to understand. So again, we are discussing about the cardinal points, and in case of cardinal points, you can see in this figure, see, if it is equal in both curvature in both side of thick lenses, then principal plane lies equal distance from the both surface. But it's central tricky. When we talking about principal planes, it always moves towards the curved surface. See, in this case, if it is plane there is no power, but in case of this front surface is highly powered, then principal plane move towards curved surface. See this figure, principal plane in third figure, principal plane moves towards the curved surface. In this plane, both curves are equal, so principal plane lies in center. But in this picture, principal plane, secondary principal move towards the curved surface. Again in this picture also, principal plane move towards the curved surface. It's always there. If principal plane is always moved towards the curved surface, but in all these pictures, every side of the refractive index of medium we consider it air, that lenses are in air. If outside of the system and inside of the system has different refractive index, then sometimes we can have like this: secondary principal plane is here and primary principal plane is here, sorry. So it can reverse in difficult cases, but not in normal cases. It's always primary principal plane is in front and secondary principal plane is always back side of the lenses, but it can swipe up when things differ, if refractive indexes differ. So so nodal point, which is very important, cardinal points, and we always take measurement of angle, refractive angle, visual acuity, angle, minimum angle of refraction, minimum angle of deviation, and all the things we take consider of nodal points. So when we talk about nodal points, the graphically extending incident and emerging ray towards the inside of the lens will interact with the optical axis at the primary nodal point and secondary nodal point. The ray directed toward the nodal point at certain angle will exit at the same angle. That's it's a great point we have to understand. The ray directed to the nodal point at certain angle will exit the lens at the same angle. So that's why we always call nodal point with angular constancy, which is angular constancy, or another way we say angular, sorry, angular magnification is 1, so there is no magnification. If nodal point at a certain angle, it will exit at the same angle, so angular constancy or angular magnification is equal to 1 when you talk about the nodal point. Nodal point coincide with the principal point when the optical axis is bound both sides by the medium of a same refractive index. See, this points comes in optics again and again, because nodal point coincide with the principal point only when if lens is surrounding both side of the lens is surrounded by simple same medium, no matter what, it's air or water or anything, but it has to surrounded by the same medium. If it's surrounding one side of the lens surrounded by one medium and another side of the lens surrounded by another medium, then it will be problematic. So you have to understand. So our eye is like that, isn't it? One side is air, outside of air, and in our eyes the refractive index is different. So by this point we can understand that it's very important that our principal point and our nodal point do not match with each other. It's very simple thing to understand. And in case of our eye, the secondary focal point and primary focal point are not same, not at all. So you have to understand why it happens in our optical system. So I'll make another video for our optics of human eye, but for this point, this is it. And now move on to nodal point. So in case of nodal point, we have to understand this rays goes there, and ray, if imaginary rays hits the principal optical axis, this point is primary nodal point. And actually refraction happens in the surface, and surface goes like this and out. We extend this line backwards, and when it hits the optical axis, this is secondary principal point. All the secondary thing we see by dash, all the primary thing we see without dash. Like example, F is a primary focal point, so P is a primary principal point, N is a primary nodal point, F dash is a secondary focal point, P dash is a secondary principal point, N dash is a secondary nodal point, something like that. So this is nodal. The angle between this, so for example this angle and this angle is always constant, always constant. Angular constancy is central important concept to understand that. So, this thick lens does not have a single type of focal length. It serves the focal length as a primary equivalent focal length, secondary equivalent focal length, back vertex focal length, and front vertex focal length. So, you have to understand these things. If we consider focal length from the vertex, then it's called vertex focal length. If we consider focal length from the principal plane, then it will consider equivalent focal length. It's central important and concept to understand. So it's very important concept to understand is this: when we consider this length from the vertex, then we know this is back vertex focal length. When we consider from this point front vertex is called front vertex focal length. But when we consider from front principal plane to the focal point, it's this length is called front equivalent focal length. When we consider from secondary focal length secondary principal plane to the secondary focal point, then it's called, what do we call, back equivalent focal length. So it's central important to understand where the length is taken from, that focal length. In For the practical uh, clinical cases, we always take back vertex focal length because for the practical purposes. But in case of optics, we use equivalent focal length. So it's central important to understand what is equivalent focal length. So equivalent power of the thick lens, it's not equivalent focal length of the thick lens. Just remember this. Equivalent power of the thick lens, equivalent power can be used for Bernoulli's equation to determine the location of the image or object relevant to the principal plane. So it is always doing with the principal plane. See, equivalent power of the focal length, the power of the thick lens. This is the great formula you have to understand. This is front surface power, back surface power, thickness, refractive index, and multiplying front surface power, back surface power. This is equivalent power. This formula comes into your life again and again and again and again. You have to understand. This is minus sign. See, you this formula comes this is always called third term of the equation, and many books write it as a third term of the equation, and you have to understand the game here always changes with this third term of the equation, because what happens if thickness increases, what happens if index of refractive index increases, what happens if front surface is negative or positive, what happens if back surface is negative or positive, what happens if both surfaces is negative or positive, what happens if either surface is negative or positive, what happens if both surfaces are negative. So what happens if we make this lens thickness thinner, what happens we increase the refractive index. So you have to understand what happens if one component of the equation we change. So it's centrally important, you have to understand like this, you have to think like this, that if one component, suppose example, this is the lens form biconvex, what happens there? If this is the lens form biconcave, if this is not, this is the meniscus form and plus meniscus, what happens there? If the lens is minus meniscus, what happens there? Because f2 is more powerful than f1 and f2 is negative, then f1 is positive. What happens there? The equation, if we increase the thickness, what happens? If we increase the refractive index, what gonna be happen with the equivalent power? It's central important concept, so you have to understand this formulas very well. Okay, so this is the example of what I am saying. In this case, this is biconvex lens. What happens if biconvex lens thickness increases? Isn't it? This is the thickness for 10, 20, 30, 40, 50, 60, and 70. And what happens if one thickness increases? Then equivalent power. What happens to the equivalent power? In this thickness, equivalent power is something like the 15 diopter. But when we increases the thickness towards the 54, 40 to 50, in between 40 to 50, lens power becomes 0. Isn't it very shocking? Because blue for the refractive index is n and red for the refractive index 1.8. For 1.8 it goes rapidly down, for blue it goes around 60 thickness, then this lens power becomes 0. So it's quite a surprising that equivalent power of the lens becomes 0 even if both surfaces has equal power. I'll give you one example. Let's take example of this lens. It doesn't matter if you increase the size of the lens. Why? Because one surface is always 0, plano. So that's why f1 plus f2 minus t by n f1 into f2. This all goes into 0. So either one surface 0 plus f2, whatever f2. It doesn't matter. In this shape, it doesn't matter if you increase thickness or not. So it's really tricky, you have to understand each shape you can develop this kind of graph, and each shape when going to thickness, it will going to change. So you must understand this concept. So there is one other another formula. Just pause the video and just look at this formula, and you can understand that how you can locate the principal plane. But I'm not going to discuss about it a lot because you can find it in books, and I don't think it's very important to understand the location of the principal point, but you can just check it and just understand things slowly. So as I have previously told you that it's going to matter that surface, if surface is not equally distributed in terms of power, the more power surface can drag that principal point towards this principal point plane towards this. For example, here the principal point like equal distance from the surface, here more power surface drag the principal point, here more power surface drag the principal point. So ray tracing, I have discussed about it in my previous video, that parallel line always goes from the secondary focal point. The line that ray that passes from primary focal point always goes parallel to this, and what another from optical axis, from optical center it always goes undeviated. And here is the result of this. The Newton's equation, though we don't use it as a Newton equation in our lensometer, but many claims that lensometer is based on Newton's equation, but it's very simple. For the Newton's equation, you have to have plus lens, first important point. Again, another important point for Newton's equation, there must be same medium from either side of the lens, from this side 1 and this side 1, whatever, 1.33 or whatever. It must be equal. And the x is the distance from real object to towards the primary focal point of the lens, and x dash is the secondary focal point to the image distance. We know that. And then according to Newton's equation, it's always x into x dash is equal to f1 into f2. But we know that f1 and f2 is not different, because f1 and f2 is equal if there is same medium in both sides of the lens. So in case of, for the Newton's equation, there must be both medium have same refractive index. So till now, the main points of the presentation, as my previous videos, the sign convention must use carefully while calculation. All focal length, object distance, image distance should be taken from the principal plane if it is thick lens. The refractive medium of both sides of the lens should be considered carefully, because no matter what, I is the medium where one side is 1 and another side is 1.33. We will discuss a lot of about it in case of Goldstein eye model and all these things, and our eye is not the same. That's why we have 24 as a secondary focal point and almost 16.67 mm as a primary focal point, isn't it? Both are not the same, not at all. So this is the point. So again, my references is Michael P. Keating, which is a great book, and for starters, I suggest this book, and this is my favorite book of all time. And I think Professor George Smith is, I revere him very much. So from his book, I learn a lot. So these three books are great books for a start. So I think this is it, and I'll see you in the next video.